So let's get started. Picking up where we left off, we were at expressions. So this is an expression basically is a sequence of characters that can be evaluated to produce a value. And so the idea here is anywhere you need a value, you can always provide an expression. You need a number, you can provide a number. 4, that's an expression. It's a literal number, 4. But if you need a number at some point, right, and you can also provide 2 plus 2. That's an expression. It evaluates to 4, and that's the value you're providing. But the point is that anywhere in a Java program, and actually in just any program of any language anywhere, the idea of an expression is a sequence of characters that can be evaluated to produce a value. And anywhere you need a value, you can provide an expression that produces that value, right? So here are types of different expressions. Literal expressions are just that value, right? The value itself. Named variables, right, when they're used in a place where we expect an expression, if we provide a variable name, what we get is whatever value that variable has, right? A version of this is where the variable is a reference to an array. We can index into that array and retrieve the value of the elements in that spot in the array. And that expression will produce that as its value, right? Class and object fields are also values that we can express, right? So we haven't talked about fields much, but the idea here is that all classes and objects in Java are associated with, possibly associated with fields. And fields are basically just named values associated with that class or object. And so here, for example, is the math class. How do we know math is a class? Anyone? Who has an idea for how we know? Yes? It's uppercase, that's right. Starts with an uppercase name. So math as a class happens to have a field called pi, which is a named constant, which provides us with the value of pi. That is an expression that evaluates to 3.14, et cetera, et cetera. And then, of course, we can call a method, and the return value of a method can be the value of an expression, and therefore, that is, can be part of an expression. And of course, anything we have, anytime we have an expression that produces a value, we can combine it with another expression that produces a value using an operator like plus or minus or multiply or whatever kinds of operators the language provides us, right? All right. So let's go ahead and just kind of make sure we understand there's a little bit of a nuance. So here's an interesting question. Can a void method be part of an expression? I want you to think about it for just a few seconds, and then we'll do a little go heels call out. A void method, can that be part of an expression? If you think it says yes, we're going to say go. If you think it says no, we're going to say heels. On 3, 1, 2, 3. Yes, you said go, but most of you said heels, and that's correct. Why? I just said that a method call could be part of an expression, so why is it that a void method cannot be part of an expression? Well, there was a little bit of a trick there, right? I said a method that returns a value can be part of an expression, right? Because of expression is a sequence of characters that can be evaluated to produce a value, but a void method is specifically a method marked as void, which means that it doesn't produce a value at all. That's what a void method is. Well, if a method doesn't produce a value, then it can't be part of an expression. So methods, calling a method can be an expression or be part of an expression, but calling a method that produces a value can be an expression or part of an expression. But obviously, calling a method that doesn't produce a value cannot be part of an expression. All right, so I said we could combine expressions with operators, and we have lots of operators in the language. I'm not going to go through these in detail. Most of these should be relatively familiar, right? One thing to realize, though, is that these relational operators, they're operators. In other words, they have a left side and a right side, and then they evaluate to a value. That value, in this case, happens to be one of the Boolean values, either true or false. But they are expressions that then turn into a value, and you can use them as such, right? And so, and then of course we can take Boolean values and operate on those with the logical Boolean operators and or and not. But this one is actually pretty interesting and a good one to know and kind of learn how to use, because again, it's a mark of a little bit of a more sophisticated programming style, certainly, but also it's nice and terse and parsimonious way of solving a common problem that comes up. Often you need to construct you need to create some calculation or do some calculation where part of the calculation involves some value where if some condition is true, you want to use one value, and if it's false, you want to use a different value, right? Well, we can solve this problem in kind of a traditional programming way by declaring a local variable and then saying if and then doing our test, and then if it's true, then we set the value of the variable to be whatever we want it to be when it's true, and then otherwise we set the value of that variable to be whatever we want it to be is false. And now we have the correct value in our local variable, and now we can use that local variable in our calculation where we need it, right? But there's a much more sophisticated way to do that same exact thing, which is to use this ternary operator. It's an operator, which means that the whole thing turns into a value, and we can use it as part of a more complicated expression. The way this ternary operator works is you start off with a Boolean expression. So that's some expression or sub-expression or something in parentheses. Whatever it is, it just has to turn into either true or false. And then this question mark. And then we provide a value for what we want if it's true, and then a colon, and the value if what we want is false, right? And so then we take that whole thing will turn into one of those two values depending on the trueness or falseness of that Boolean expression. So then with that, we don't have to have a local variable and an if statement and all that business. We can just use this ternary operator right where we're trying to, where we need the value we're trying to select, the A if true, B if false. Right? So anyway, so that's kind of a nice operator to kind of keep in your little toolbox because it comes up more often than you'd think. Bitwise operators are operators that work with the individual bit patterns inside an integer. We're not going to do much of that in this class, but they're there. You should be aware of precedence. Obviously, there's like some things happen before other things. You can think of math, multiply and divide happen before plus and minus. And you should also be aware of context. And so if precedence is going to be a problem, if precedence is going to be an important part of your expression, you should use parentheses in order to make things a little bit more clear. But you should also be aware of context in the sense that some of these operators do different things depending on the types of their operands. In particular, plus will do addition if you have numerical operands, but if either side happens to be a string, then it's going to actually do string concatenation instead. So some of these operators have more than one possible meaning depending on its context. Some of these slides I'm going to go through very quickly to just allow you to kind of study on your own. Like this one, it's just a whole bunch of shortcuts for syntactic sugar for forms of adding something to a local variable, like a plus equals 3 is the same thing as a equals a plus 3. Right, and so now I want to demonstrate something that if you follow the A1 instructions, there is a link to a video that demonstrates this very thing, but basically how to take a GitHub repository that we are distributing either as the assignment link or as starter code or as lecture notes, lecture example code, and how to integrate that into your Eclipse environment. Okay? So just to demonstrate, you can follow along. Here I have started Eclipse. It's not showing the workbench. It's showing the kind of the splash page. So I'm going to go to my workbench. Here's my workbench. I'm going to throw this away. That's no big deal. All right. Let's see if this works. The first thing I want to do is I want to create a local clone the repository locally in a way that Eclipse can know about it, right? So you may or may not have a lot of experience with Git, so we only need a few specific, easy kind of operations. So we don't have to do terribly sophisticated things. So if you don't know Git, that's fine. You can just kind of follow along on the one or two things that we need to do. But the first thing we need to do is to clone our GitHub repository in a way that Eclipse is aware of it, right? So the way to do that is to first go to get the clone URL for the repository you're trying to clone. So in the code that we distribute, if we go to our Sakai page, for example, there is this repository links for lecture code examples. And if we go there, we can see that there's a couple of links here already for lecture 2 example code and lecture 3 example code. Since we're picking up actually in the lecture 2, the middle of lecture 2, we're going to go there. That'll take you to the GitHub page for this repository. And this clone or download button will give you the URL, which you can copy. Okay? Once you've copied the URL, the clone URL for the repository, we need to clone that repository, and there's a way to do that through Eclipse so that Eclipse also knows about that repository. And the way to do that first is to bring up the Git repository panel on Eclipse. It's not a standard panel that shows up when you first start Eclipse. So to get to it, you go to Window, and then Show View. And then let's see here if this works. Oh, no, it doesn't work. Oh, yeah, it does work. Look at that. Woohoo! All right, Show View. And then it's not one of the common ones. You have to go all the way to Other. And then here, there's all the different panels that Eclipse has. And there's a whole bunch of Git panels. The one we want is this Git repository panel. And that brings up the Git repository panel, which we can see is over here, right? So this Git repository panel allows us to add repositories, clone repositories, in a way that Eclipse knows about it. So right now, my Eclipse doesn't know about any repositories, so I'm going to click this little button here for cloning a Git repository. That's going to bring up, sometimes they'll ask you for your password, especially on a Mac. So whatever your operating system wants you to do that. Here's the little dialog box. Here's where you put that URL that we copied from GitHub, right? That clone URL. If it's already on your clipboard, this is kind of smart. It recognizes it and it'll pre-fill it. If it wasn't there already, that's where you paste it. When you paste it there, it'll parse it and it'll know, oh, I need to contact github.com. Here's the name of the repository path. And then here's where it's going to ask you for your Git credentials. You only have to do this once if you store them in Eclipse. If you don't want to store them in Eclipse, then you'll have to do it every time. But you provide your Git credentials there. Then go next. Here's where it'll show you all the branches of that repository that are available. Just select them all, usually. Like you want the whole repository. So say next. And then it's going to ask you for a local destination. So it's going to put this repository, it's going to clone, right, this repository somewhere on your hard drive. And it's asking you, where do you want to put it? Now, it'll pre-fill this with a spot which is like its standard spot. But if you want it somewhere else, you can put it somewhere else. The only thing that's important is you need to be able to get back to wherever it gets put, because that's going to be important for the next step. I'm going to put it somewhere other than the normal spot. I'm going to create a new folder in my here. Okay, I'm going to put it here. Great. And then I'm going to say finish. And then what it'll do is it will go get that repository, and you can see inside this Git repositories panel, there's the repository. And it says you're on the master branch, and it has all kinds of information and about branches and tags and all this Git stuff, and you can do anything Git related to this repository through this panel, through that interface. We won't need to do much, but if you're really into Git, then there it is, right? So while this creates the repository locally and now puts it into Eclipse in a way that Eclipse knows about this repository, what we haven't done is we haven't created a project yet, right? So we can't really run or work with the code in that repository. We have to create an Eclipse project from that repository. There's more than one way to do this, but I'm going to do it the way that I know will always work, which is to right-click on the Package Explorer or go to File, New, either way, and say New Java Project. And then in the project name, right? Don't provide a project name. Instead, unclick this use default location, and then browse and go find wherever your repository got put, right? So wherever that you clone the repository, go find that folder where the repository was cloned into. So in this case, right, for me, right, it's already here, but like I happen to put it here. There it is. There's the repository that we just cloned. So I'm going to click on that. And that is what I'm going to select as the location for the project. And then if you say finish, then we'd never create a module, so don't create. Then we can see what it'll do is it'll create a new project in our Package Explorer, and you'll know it's correct because it'll have the same name as the repository, and just like here the repository says what branch it's on the master branch, you'll see that Lecture 2 master branch information in the project name, right? That's how you know you've created a project from a repository correctly, right? And then if we look in there, there's all our code that we got from the repository. All right. Okay, so we did that in order to get to this example, which is going to demonstrate a bunch of things, right? So this example, if we look at the code, it's just there's just a bunch of comments and small bits of code demonstrating some of these things about integer math and the tertiary operator, and that kind of stuff. So what I want you guys to do is to take just a couple minutes to go through that code, look through it, share it with your neighbor, make sure you understand each little bit, like there's little comments, make sure you understand the comment as it relates to the code below it. And then when you're done, go to typeit.dev and do the Lecture 3 Interlude 1 in typeit.dev. And while you're doing that, I'm going to give you about 3 minutes to kind of do all that. I'll do the typeit exercise on the screen. All right, so go for it. All right. All right, great. All right, so let's taking a look at the code, just what you saw. I'm just going to first open it up to questions. Anything about the code that was in this example that anyone wants to ask a question about? All right, so it's good. I'm ready to go. Just whip on through? Right, all right. So, okay, I'm just going to point out a couple of things. One is that integer math, right? That's one thing that some of you may not be kind of used to if you come from a language that doesn't make a distinction between integers and real numbers. In Java, when you do integer math, you get an integer result. And even if it's part of some sub-expression that is then going to be, mixed with real numbers. So for example, if I have 7 divided by 8 plus 2.0, I'm going to get 2.0 as my answer. And the reason why, not 2.87825. And the reason why is because the 7 divided by 8, if it's an integer 7 divided by an integer 8, and since that is happening first because of operator precedence, that operator is operating on 2 integers and therefore will produce an integer. 7 divided by 8 is 0 in integer math because there is no fractional part. And then I'm going to do the 0 as an integer plus the 2.0 as a real number. At that point, because one of my operands is real, I'll get a real result. But by then, the mistake is already made, right? You've already had a problem. So just be careful that when you use integers in mathematical expressions, sometimes it's exactly what you want, that integer math kind of semantics, but sometimes it kind of creeps in to some larger expression in kind of surprising ways because you didn't really realize that some portion of your expression was going to end up truncating the integer, the fractional part before it got combined or used in with some real number. So when you mix integers with real numbers in some mathematical expression, make sure that those integers are interpreted as real numbers. One way to do that is to cast them explicitly. The type it exercise has a version of this. So what that looks like is, let's see here, where was it? Yeah, right there, right? That's a way to force A to be a double before it then gets used. Another common way to do it is to multiply the integer by 1.0 in order to then create a double result before then using it. So that's one thing I wanted to point out. Another thing, there's a nice example of using the ternary operator in order to select between two values. Here we're selecting between the string heels and the string devils based on the expression in front of the question mark. And so we get one of those two values as the result of that expression, which then gets set to, a reference to which gets set as winner, right? So the only thing to point out there is when you use this operator, the two things that you're deciding between have to be the same type. And that makes sense, because you're either going to get the first one or the second one, and whichever one you get, that value then is going to get used either as part of a larger expression or part of an assignment statement or something like that. And the type of both options has to be the same. Operator precedence, I think you guys are probably pretty familiar with. One thing to note here, this last bit kind of demonstrates this, is this notion of short-circuiting with Boolean operators. With Boolean operators, the left-hand side gets evaluated first, and if it's true or false, if that alone is enough to know what the result of the Boolean operator is, then the right-hand side will not get evaluated at all. So if I have something that's false and I'm ANDing it with something that's true, as soon as I know that the left-hand side is false, the right-hand side never gets evaluated because the AND operator already knows that the answer is going to be false. The opposite is true is the case with OR. If the left-hand side is true, then the OR operator never does the right-hand side. If the expression on the right-hand side has some sort of side effect or or does something other than just produce a value, this short-circuiting effect could prevent that thing from happening because it never got evaluated. So that's another thing to know. Okay. Getting back to things. Okay, so right. So we can obviously inside a method like this, what we've been doing is just kind of learning a little bit about the kind of the nuts and bolts of Java statements that we use to build actual procedures and methods for our program. So we've already seen how to declare local variables and how to assign them to values. We've seen the idea of values. Anywhere you need a value, you can have an expression, and we've seen a few things related to that. The next thing we're going to look at is conditional execution. Every programming language, and in fact, you can argue you can't be a programming language unless you have conditional execution. That it is, in fact, the one thing that makes a programming environment different than just a calculator, is that you can say, if something is true, do one thing, but if it's not, do something else. As soon as you have that construct in your computational environment, you have a programming language, right? It's almost the only thing a programming language absolutely must have, right? And so this is traditionally an if-else kind of statement, and Java has that, just like most programming languages have that. The syntax of Java's is this, where we say if, and then in parentheses, an expression, and we know what that is now. It is a sequence of characters that can be evaluated to produce a value, right? But in particular, it needs to be a Boolean expression. That expression must return not return, but must evaluate to either one of true or false. It has to produce a Boolean value. No other kind of value will work. So if you put an expression in an if statement that evaluates to a number, it's not going to work. Because unlike other programming languages, Java does, when it expects a Boolean expression, it expects a Boolean expression. It expects that expression to produce one of the two Boolean values. Other programming languages, when it gets a non-Boolean value in a place where it expects a Boolean, have rules for how to turn that into either true or false. So a common one for C, for example, is if it's 0, then it's false. If it's not 0, then it's true, right? Or in some languages, if that expression had produced a string, if the string was empty, then it's false. And if it's non-empty, if it has a length, then it's true. But not in Java. In Java, if you have a number that you want to say is 0 or not 0, then you have to say double equals 0 in order to then have an expression that is either true or false. If you want a string and test how many characters it is, you have to get the length of the string and test it against it being 0 in order to get an expression that is either true or false. But once we have an expression that is either true or false, we either do the block of code or we go to the next part of the statement, right? So we can chain else ifs together if we want, as many as we want. If we want kind of first test if this is true, if that's not true, then the next thing if that's not true, until we find one that is. And then, of course, we can have a trailing else that catches everything else if it never evaluates to true. And those parts are, of course, not mandatory, right? If you just want to do something if something is true, and then if it's false, there's no other thing to do, then you could just have the first part of that statement. Here's an example. I'm not going to belabor it. You can kind of read it on your own. There's another fancier version of essentially an if-else-if statement called a switch. You never have to use a switch. A switch doesn't give you any more power than an if-else-if does. There are some cases where it'll be easier to read, easier to write, or otherwise, avoid having to repeat lines. But otherwise, it's just a fancy version of if. The way it works, quite briefly, is that the expression is evaluated and it produces a value, not necessarily a Boolean value, any value, but it only works with the primitive value, so it's got to be one of the primitive value types, or it also works with something called enumerations, which we'll get to later, and strings. But in any case, you produce a value, and then inside the body of the switch, you can have one or more case statements where you provide specific values. And what basically the idea here is we evaluate the expression, we get a value, and then we go from case statement to case statement looking for a match. And then wherever we find a match, that's where we start execution. And we keep going until we execute everything from that point forward until either we get to the very bottom of the switch statement, or we hit a break statement. So the most common way to deal with it, to see this, is to see a bunch of cases with various statements below each case statement separated by break statements so that they don't fall into each other, with possibly one last case called default, which is a keyword, which is basically none of the above cases matched. You don't have to have a default if there's no default to be had. You can do fancy things like have one case start and like have statements associated with one case and then not encounter a break statement and then fall into the next case. So if you have a situation in which if the value is A, you want to do these first 7 statements and then following another 5 statements. But if the value is B, you just want to do the last 5 statements. You can do that with the switch statement by creating a case A and then having your first 7 that are specific to A, things that you're doing, and then have a case B and then have the 5 things that both A and B do. Then if it's A, it'll start with the case A, run through, do those first 7s, just keep going right into the case B and then do the next 5. And if it's case B, then it'll just start right before the 5 things you want to do if the value is B. Again, you don't really ever have to use a switch. It's just a fancy version of an if-else-if, but you can play with it and get used to it. It can be kind of nice sometimes. All right. All right. So now we have example 3. And then I'm going to give you a couple of minutes to look at it, and then we'll go over it. Why does this not? There we go. Sorry about that. I think this is, let's see if that works. Nope, that got worse. All right, great. OK. So in this example 3, again, it just kind of demonstrates a few of the things I just went over. If statements. I want to point out a few small little style issues and kind of common mistakes. One common mistake is to test for a Boolean expression like this by saying something and then double equals true. Never, ever should you ever have to say double equals true. Or, for that matter, double equals false. Okay? Because, and the reason why is because double equals is a relational operator that basically says if the thing on the left-hand side is equal to the thing on the right-hand side, then be true, otherwise be false. If you already have a Boolean value, then double equals doesn't really do anything for you. If you're saying the thing on the left-hand side is double equals true, well, if it was true, you already had the value true. You didn't have to say double equals true. The thing on the left-hand side just was true already, right? Now, how about if you want to say, well, what I'm really looking for is whether something's false. Then I would need the double equals because I want to know that it is false, right? Well, yes, but no. The way to deal with that is to simply take whatever it is you're trying to say double equals false, the thing on the left-hand side, and use the not operator to invert it. If it was false, then not that is in fact true. That's the same thing as saying what's on the left-hand side double equals false. Because that expression will be true if the thing on the left-hand side is false. Well, I can just take the thing on the left-hand side and put the not operator in front of it. And so now, if the thing on the left-hand side was false, not false, that's true, right? So just stylistically, you should never, ever have double equals true or double equals false. Instead, if you're interested whether this is true or not, you already have it. It is true. So this is the better way to write that kind of statement. If you want to know that the thing is false, then instead of saying check in positive double equals false, just say bang, check it positive, right? Here's the not operator, that exclamation point, right? So that will just invert it, and so now you've turned your false into a true, and you're good again, right? So that's one common little mistake that beginning programmers make a lot, is to use the double equals operator against the Boolean literal true or false. There really should never be a need to do that. An example of a switch and its corresponding if. I'll let you read that on your own. Here is an important point that I want to get across, which is that when you are trying to compare two real values for equality, not compare them for being less than or greater than each other, that's fine. But when you're trying to compare two real values for equality, you never, ever use double equals, right? We use double equals all the time for integer values because integers are integers and 4 is 4 is 4 is 4, right? But with real values, it turns out 4 is not always 4. 4 is sometimes 3.999999999 forever, right? And the problem here is that with fractional values, with real values, you can get to a point where the result of your calculation in your mind, like in infinite precision math, should be 3 or should be whatever value it is, right? But because you arrived at that value through some set of operations involving real numbers in a computer where we don't have infinite precision, we have to cut it off at some point, you end up with a number that's really, really close to the number you would have gotten with infinite precision, but you don't get that number quite. So here's an easy way to think about it, or a kind of a more relatable way of thinking about it. Think about 1/3, right? We think in our minds, 1/3, that's 0.33333. Well, when does it end? It never ends. It's 0.333 with the bar of it, right? It's a continuous fraction. It goes on forever. But if we see 1/3 plus 1/3 plus 1/3, we know that that's 1. Right? And so, we know how, we know that each of those is this infinite precision, continuous fraction, and that we can add those together, and it can get to something that doesn't continue forever, that actually stops, like 1/3 plus 1/3 plus 1/3 equals 1. So the same kind of thing happens in binary math inside computers, right? It turns out that 0.1, for example, in binary, right, as is a continuous fraction. And so 0.1 plus 0.1 plus 0.1 in a computer will not exactly equal 0.3. Instead, it's going to equal 0.299999999 all the way until whenever you run out of precision. So if you have two values, one which you arrived at more directly, 0.3, the other you arrived at as a result of some operations on real numbers where you might have had this precision loss, right? If you try to double equals those numbers together, they will not be equal, right? And this is particularly, can bite you when you're in this situation where in decimal, in a base 10 way, there's no continuous fraction, so you're not, aware or thinking that, hey, these two things might not equal each other exactly. But in terms of base 2, it turns out one of the fractions you used was continuous, and therefore it didn't actually add up altogether correctly. Instead, whenever you have a situation where you have two real values that need to be compared for equality, you must decide how close is close enough, and compare them by taking the absolute value of their differences and comparing it against whatever precision test is appropriate for the piece of software or the situation that you are writing. Right? And so you really need to do it more like this, where you say math.abs. That's basically absolute value method that's available in the math class. I'm taking a minus b, I'm sending it to the absolute value method in the math class in order to get the absolute value, and I'm comparing that against, right, a less than, to see what that is less than, and here is where I have chosen how close enough needs to be. Now, how do you choose that number? That depends on the context of your software. If you're doing something like a game and you just need to know whether something hit something else, then maybe you're within half a pixel of each other, then it's a collision. So maybe these are two distances you're comparing, and you just need it to be within a half of each other. That could be good enough for that game, right? If you're doing some sort of weather, kind of a simulation or modeling a nuclear explosion, you probably want something a little bit more precise, right? But in any case, you have to decide. So it is never OK to say double equals between two real values. You must always compare them against some sort of precision bound, or epsilon bound is another term for it. And if you're going to do it a lot, then you might as well create a little helper function. Here's one that basically will return true or false, depending on whether A and B are within a bound or not. And you can see here, I've just created a little expression. Left-hand side less than right-hand side, then that expression is either true or false. So that is what I'm returning. And so I can use that up here in order to compare whether A and B are equal, true, or not equal, false. Right. All right. OK. So now we've covered a few of those things. Let's do a little Gohil's call out here. So think about this for a second. Which of these is the better way to write an if statement, assuming that got milk as a method is going to return a Boolean value, right? So, right? OK, think about it. All right, on three. 1, 2, 3. Yes, exactly. You never say double equals false, right? One more, or this one we won't have a call out, but we'll just have a little fun here. ¿Quién es más macho? Antonio Banderas or Ricardo Montalban, right? So here we're basically doing the same thing. We're trying to decide whether a particular distance is a short run or a long run, and we can just going to read it for a second. And then if somebody wants to offer an answer, anyone? Oh, come on. Yes, yeah, there you go. Dígame, ¿quién es más macho? Ricardo Montalban, indeed, right? Because we're using a absolute value bound on the precision. Exactly right. We don't want to say double equals in a situation where we're using real numbers. OK. Moving on, we have looping, right? So if statement is if conditional execution is the foundational thing you absolutely must have for a programming language, loops are a close second. Technically, you don't have to have a loop in order to have a programming language, but it makes things a lot easier. So almost every programming language does, and so does Java. And presumably, you are familiar with some sort of looping mechanism in the whatever programming experience you have. In Java, we have while loops and for loops. While loops are kind of the simpler one. They look like this. Basically, a Boolean expression. It's either true or false. If it's true, we execute the block of statements. And then we go back to the top and we reevaluate the expression. There's a presumption that the way this is working is that something about that expression is going to change or might change each time through the loop. And then we just keep going until finally that expression comes out as false, and then we're done, and then we pick up the program past the while statement. Right? If you want to make sure that the block gets done at least once before the expression is evaluated, you can kind of write it in this other form where the expression's at the bottom. But that's actually fairly rare. I mean, I never really see that come up in real situations, but it's there. So for example, here is a while loop that sums the numbers between 1 and 10, right? We start off with the summing variable that we set to 0 and a counting variable that we set to 1. We have our condition, n is less than 11. If that's true, then we add n to sum and then increment n. And we go back to the top. We look at n again. Okay, that's going to happen 10 times. Once n becomes 11, less than 11 is no longer going to be true, so we'll stop, and then we'll pick up at the print line statement where we'll print out the sum from 1 to 10. Right? So fairly simple. and hopefully familiar enough with respect to some looping construct that you're familiar with in some other language. A for loop is a little bit different, but technically, a for loop really is just syntactic sugar for a specific kind of while loop. So it doesn't add any real power. It just comes up so often that often most programming languages provide a for loop form just because it does come up so often. So the idea here behind a for loop is you're taking some variable, almost invariably an integer, but it doesn't have to be, but like almost always it's going to be some sort of integer, and you're running it through some range of values, a loop counter, and then going through the statement block that many times. So you can set this up in lots of interesting and sophisticated ways, but the very, very most common thing that you're going to do with a for loop is you're going to run an integer from 0 up to the length of an array, and then inside the block of statements, you're going to do something with each element in that array, right? Or scan through that array looking for something. That is like 90% of for loops everywhere are basically being used for that, right? So a for loop has the following structure. Inside the parentheses are 3 parts separated by semicolon. The first part is an initialization statement. Usually there is where you declare and initialize your looping counter. Then you have your test. That's where you have a Boolean expression that often is used with your looping counter, usually. I mean, again, you can use it however you find useful. You don't have to use it for that, but that's really the most common case, where you're going to test that looping counter against some limit. And if it's true, if that test is true, you'll execute the statement block. And at the end of the statement block, you'll go back up to the top, and then you'll do the third part of the for loop, which is the update statement. And that update statement will execute, and usually that update statement is going to update your looping counter. Then you'll go back and redo your test. If it's still true, then you keep doing this over and over again. So the init statement happens once at the very beginning before the first test, and then the update statement happens once just before the second time you do the test, and every subsequent time you do the test, right? So initialize, test, if true, do the statement block, update, test, if true, do the statement block, update, test, if true, do the statement block, over and over again until finally the test comes out false, and then you pick up after the for statement. Right? So that very same while loop could be rewritten as this for loop, where I start off with my summing variable as int sum equals 0. And now notice, instead of having a local variable n outside of my loop, I am now declaring that int n inside my for loop. This is nice because it limits the scope of this variable to just be the for loop. That helps reduce bugs and keeps my local variable useful only where I meant it to be useful, right? So here I'm initializing my integer n to be 1. That's my initialization statement. My test is whether n is less than 11. My block of statements adds n to sum. And then to update n, I do n++ to increment n. And then I keep doing that 10 times, right? There are, in both while loops and for loops, you can, in the body of the loop, be a little bit more sophisticated about whether you continue or not. In other words, in the body of the loop, if you ever get to a point where I want to go back to the top of the loop and either update the looping counter and redo my test, or in the case of a while loop, just evaluate my test and skip the rest of the block and go to the next iteration, if you will. You can do that with a continue statement. That's relatively rare, but sometimes it's useful. But more commonly, you're trying to break out of a loop early. In other words, you've got a loop that you're going through, let's say an array, and you're looking for a value. Once you find the value, you don't have to keep going. You don't have to keep going through the rest of the values. You can stop. And so if you want to break out of the for loop early, you can use a break statement. Same thing with a while loop. If you find yourself in the while statement block in a situation where you know that, oh, right, I'm done now, I need to break out of the while loop and then keep going with my program, a break statement will do that. All right. Okay. So let's do example 4 here. I was going to give you time to kind of do it on your own and to maybe do the interlude 2 on type it, but we're running a little bit behind, so I want to kind of keep going. So I'm just going to show you example 4 and point out a few things, but you should study that at home. All right, so here I show the equivalence between for loops and while loops. Here's the exact same example from the slides. Here's the summing 10 by as a for loop. Here's the exact same thing using a different local variable name just so that it doesn't conflict as a while loop. Here is a kind of contrived example that demonstrates break and continue. If you look through this code, you can see that what it does is this math.random, that's a class method inside the a math class method that will produce a random value between 0 and 1 as a double value. And we can see what we're doing is we have this summing variable dsum here, and we're drawing a random number, and as long as that random number, if that random number is too big or too small, right, that's what this if statement is doing. If it's greater than 0.9 or less than 0.1, then I'm just going to continue. In other words, skip all of this stuff. If I hit this continue statement, it just skips everything and goes back to the beginning of the loop and reevaluates. So if R is too small or too big, it'll skip this and go back up. It'll increment number of tries and then test whether or not I've done this 10 times or not, right? Because I'm starting off with tries being 0. If I do pick a random number between 0.1 and 0.9, so I don't continue, then I add that to my sum, and now if my sum is greater than 5, then I'm done. That's the point of this, to try to get to 5 inside 10 tries, and then so if I want to be done, I can break. And so regardless of which iteration I'm in where this is true, I will stop and pick up at the print line. So it kind of shows a demonstration of continue and break. All right. I mean, you can run this if you want. It's not all that interesting. Right, so we're here, this one, this is great. Okay, so I just ran it. We just got this result here, collected a sum of 4.3266 blah, blah, blah in 10 tries. Right, so here's the question. The question is, did we hit either the continue or the break statement? Do we know we hit the continue? Just by looking at that output, do we know that we hit the continue or not? Anyone want to gather an answer, whether we absolutely know we hit the continue or didn't hit the continue? We don't know, right? Because there's nothing about that output that tells us whether or not during one of those iterations we picked a random number that was too small or too big and had to continue. Do we know whether we hit the break statement or not? Yeah, we do know we hit the break statement. No, actually, we know when we hit the break statement. Did we hit the break statement or not? Some people say yes, some people say no. Let's think about it a little bit. The answer happens to be no, we did not hit the break statement. Why? Because we would have only hit that break statement if, while we were trying our 10 tries of random numbers and summing them, we got to a sum that was greater than 5. If we look at our output, it says we collected a sum of 4.32 in 10 tries. In other words, we took all 10 of our tries. The only reason we left the for loop was because we were out of tries. We ended up doing it 10 times. We never collected a sum greater than 5. So we know we never hit that break statement, right? From just looking at how the code is structured. If we had hit that break statement, the number of tries would have been either smaller than 10, or if it happens to be 10, we know that we would have hit that sum on exactly the 10th try. So if we do it again, nope, 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 nope. Wow, this is a gambling game that's easy to predict. Huh, I would have thought, isn't the expected average of the 10 random numbers to be 5? How are we not getting anything higher than 5? That's weird. Okay. I'm not going to figure it out. Let's keep going. All right. Okay. I'm going to skip this call out so that we can keep going because there's some other stuff that I really want to make sure we get to. All right, so another thing we can do inside a method, right, besides declare local variables and assign them values, possibly do conditional execution in an if statement, or possibly do some sort of looping construct, is we can call other methods, right? We can be in one method and then call some other method, either to produce some value that we then need as part of some expression, or for the side effects of that method, like as a procedure, right? One way or the other, like there are often cases where we need to call some other method. Or if we have a recursive function, maybe we have to call ourselves because we're trying to recurse down to our base case. But in any case, we might have in a method, one of the things we may need to do is call another method. So to call a method is relatively simple. We've seen a few examples already, and presumably you've done something similar in some other programming language. To call a method that's defined in the same class, all we need is to provide the method name, an open parentheses, and then a list of values, or expression of values, expressions that produce values that match our parameters, right? If the method needs 3 parameters, and the first thing's a string, and the second thing's an integer, and the last thing's a double, then I have to provide whatever the values that method is expecting in the appropriate type and in the appropriate sequence, right? So that's fair enough. That's easy enough. We've seen that already. If you want to call a method in another class that is in the same package, then all you need to do, you can still do that, but you need to have a more qualified name. Because it's not defined in the class that you're in, it's defined in some other class, the name of the method has to be preceded by the name of the class separated with a dot. So in other words, I have to say the class where that method exists, dot, then the method name, and now I can call that method, right? We've seen that with math.abs for the absolute value method in the math class. This usually only works for classes that are in the same package. Math is special, right? I'll talk about that later. You know, if you have a class that's in the same package and you want to call one of its methods, its static methods, its class methods, then you can do that with the class name dot method and then whatever the values you need to pass. If the method is in a class that's in a different package, you can still do it, but now you have to have a fully qualified name. You have to start with the package name, and then a dot, then the class name, then a dot, then the method name, and now you can call that method. So it's always available. I mean, like, you know, it's not that you can't call a method of a class that's not in the same package. It's just more of a pain in the ass, right? Just because you have to provide the fully qualified name. And obviously, you know, and like the last point down here below is just that, you know, you can use calling a method as part of an expression if it returns a value, and then just, you know, use that value as the value of that part of the expression, right? With the caveat that if you have a void method, then a void method cannot be part of an expression because it doesn't produce a value. Right? We can have return, or the return statement is basically the last kind of statement you might have in a method is where you're at some point where now you need to return the value that the method is going to return. You've calculated the answer, you've come up with the thing that the method is trying to produce, and you need to return it to whoever called that method, right? Like, you're always in some method. You know, either you got called by some other method, or you're in main, one way or the other. You're in some method somewhere, and so you know, if this particular method is now done and needs to return its value to whoever called it, then we can use a return statement. And if if it's a void method and it doesn't have any value to return, then you just say return with the semicolon. All right. This last example, I'm not going to go through. I'm going to let you guys go through on your own. It basically demonstrates calling methods and demonstrating return. It also has a bit where it shows you that the compiler is kind of smart. If you arrange your code in such a way, if you put a return statement somewhere and then have statements after that return that can never be reached, the compiler won't let you keep going. It'll point that out as an error, like it can't possibly be right because you have unreachable code. So that's something that this example shows. And it also shows the use of an import statement where if we look at calling methods, I said if you wanted to call a method in a different package, in a class in a different package, you had to use a fully qualified name. That can get kind of cumbersome. So you can import class names from another package. It doesn't mean that they're becoming part of your package. It just means that those class names can be referred to as if they were in your package so that you don't have to fully qualify their names. It demonstrates using the import statement. It turns out that that all the classes that are part of the standard library, like math, for example, are always imported into your namespace all the time. So you don't have to say import java.lang, which happens to be the name of the package that the math class is in, which is why our math.absolute or our math.random work just fine. Because all of the base language classes that are in the base language package, which happens to be called java.lang, are imported automatically. So, but if you're trying to use classes that are in other packages that are not the base Java language package, then you can make your life easier by saying import from that package whatever class name you need to use, so that in your code in that particular spot, in that particular in that particular class, you don't have to use fully qualified names. Again, I'm going to let you kind of look at that on your own, right? So that we can get to some more interesting things, right? So that's kind of syntax, right? Everything I've described there is just the atoms, right? The basic Lego pieces that go into building procedures and functions, which are kind of our base unit of programming, right? We start off in a main method, and we have code that is these things to do what we need to do, and sometimes we'll create helper methods or other methods to do other things, and combine all these things up together in some big program. So everything we've talked about up to now should have been fairly familiar in one guise or another from whatever programming environment you're coming from. So now we're going to start to talk a little bit more about things that are a little bit more Java specific, in particular the idea of objects, right? So we know that we have these two different kinds of types. We have the value types, which are just values, right? The 4 different kinds of integers, 2 different kinds of real numbers, Boolean and character. Those are just values, right? And so, and they are what they are, right? They're just bit patterns, that we can name, right? They give variable types to. Then everything else that's not one of those basic primitive value types is a reference type. It means it's an object. It means it's a structure in memory, right? There are some things that all objects in Java have in common, like they behave in some ways. All objects have certain kind of semantics and ways of behaving that are just part of how Java does objects. And so what we're going to do is we're going to look at string as an example of an object, right? So strings are objects in Java. Right? So individual characters are value types, right? The character C, but a string is a sequence of 0 or more characters, and that is an object. That's a structure in memory, right? So, so strings are objects. Objects have a type. In the case of string, the type of a string object is string with a capital S. Just like we have class names that start with a capital S, and these object type names start with with a capital letter, that should tell you something. An object's type is a specific class. And in fact, the way we've been using Java so far, just as a collection of static methods, is not how we generally will program in Java most of the time. Most of the time, we're using classes in order to define new types, so that we can create objects of that type and then manipulate and work with them, right? So the type of an object is the class that produced it. So there is a string class, and it is capable of creating new string objects, right? And so all classes, right, not all classes, but in general, most classes are written in order to be factories for new objects of that type. So objects have a type, right? And those types are reference types. That means that if I have a string variable a, that a, right, is a reference to some string in memory. I can change that reference to be a different string in memory, but basically I'm making the reference change. Like first it pointed to this string in memory, and now if I say, so a equals hello, great, there's a hello string somewhere in memory, and that's a is referring to that spot in memory where that hello string lives. And then later on in my program, if I say a equals bye or a equals see you later, right? But what I'm essentially doing is it's the same named value, right? But the value of that the value of that name a is being changed from instead of being a reference to the original string, it's now a reference to a different string. So the strings themselves, those are in memory, and their memory addresses is the reference that the named variable that has the right type is referring to either one object or another object. Right. So here's the part that we start to now encounter Java a little bit more the way it's supposed to be programmed. Objects can also have methods. Up to now, we've only been dealing with class methods, basically methods that belong to the class as a whole. And so those are the ones where we use the static keyword in order to define them. And then we can use them just by using the class name, math.abs, for example, math.sqrt for square root, math.random for random. Those are class methods defined in the math class, and I can just use them through the math class name. If I have instance methods, remember we haven't really written those or really looked at those. If I have instance methods as part of a class, those methods can only be invoked in the context of a specific object. So string objects, for example, have a number of instance methods that will operate only in the context of a specific string. So I can't say string with a capital S dot length, because that doesn't make any sense, right? What string, right? I can't ask the class as a whole for its length. I need to ask a specific string for its length. So the length method is defined as an instance method, which means that we have to have a instance, sorry, I need to be able to see my pointer. Right? So we have to have a specific instance of S in order to ask it for its length. So here I have a string S. So S is a named value. So there's a variable, right, S. The value of that variable S is a reference. It's a pointer. It's a memory address of this literal string. This is a string. So this literal string, that creates the object in memory somewhere. And now S points to wherever that object is living in memory. And now, if I want to know how long that string is, I can take S, right? That's the reference to my specific string, then dot, the dereferencing operator, and then the name of an instance method, right? And instance methods only make sense in the context of a specific object. So you can't say string.length, capital S string.length. That doesn't make any sense. You can't ask the class what its length is. You need to ask a specific string what its length is. Just like classes can have fields, name fields like math.py, objects can have fields, and we'll get into that because that's data structures. Essentially, an object is a basic data structure. It's the first one we're ever going to encounter, and we'll deal with it in a week or so. Right, an object can have a named value that is a field that's part of that specific object. And we get to it just the same way we get to the methods, with a reference to the object, dot, and then the field name. So if you see parentheses, you know that you're calling a method on the object. If you don't see parentheses, then you know that you're accessing a specific field of that object. But either way, the syntax is the same. The left-hand side needs to be the name, a reference to the object you're working with, and the right-hand side is either a method associated with that object or a field associated with that specific object. To create strings, we usually create them as literals because we can type, right? So we can say string s equals, and then open double quote, and then put whatever string we want, and then close double quotes. So for string in particular, we just use literals a lot of the time, or we construct a string, build a string out of its parts by using the plus operator to concatenate strings together, or something like that. However, you can also use something known as the new operator in order to create a new string, right? Now that's the normal way of creating an object. So strings are a little bit special. We almost never use the new operator with strings in order to create an object, but we usually use the new operator with all the other kinds of objects in order to create new versions of that object. All right. Okay. So there is an example here. Oh, all right. So the next example is in the next lecture, and we're running out of time. So